Hello everyone, welcome to this video. In this video, we shall discuss two alternative proofs of one of the most fundamental theorems of number theory, which can be stated as simply as this. Number of primes is infinite, or the cardinality of the set of prime numbers is infinite. So I shall begin with a proof that all of you know, and I'm sure all of you have seen. So the proof goes as follows. So this proof is due to Euclid. So suppose there are only k many primes, and let P1 equal to 2, P2, P3, all the way up to Pk be an enumeration of all the primes. All right. So basically, P1 equal to 2, P2 equal to 3, P3 equal to 5, and so on. All right. Now define n equal to product of all the primes that you have enumerated and add 1 to it. Okay. So n is essentially P1, P2, P3, all the way up to Pk plus 1. All right. So now we know that every natural number has a prime divisor greater than 1. So assume that n has a prime divisor p greater than 1. Now, the crucial observation is that notice that p cannot be equal to any of p1 through pk, because if p equal to pi for some I in 1, 2, 3, k, then pi will divide, since p divides n and p is pi, so pi divides p1, p2, all the way up to pk plus 1. Okay. So that will in turn imply that pi divides 1, which is not possible. So p, the prime factor or the prime divisor of n, is a prime which is not present in our enumeration. Okay. So such a construction shows that number of primes cannot be finite. So essentially, Euclid's proof was almost same, but he didn't enumerate all the primes. He worked with finite subsets of primes. Okay, so essentially same argument. Anyway, so this was the elementary proof that you have all seen. But what is more interesting and elegant is two beautiful proofs due to Arpan Shadukan. So he is a graduate of BSET from my side. He graduated in 2016. He's one of my seniors. So before we look into his ingenious proofs, we need to introduce some notation. So the first point is essentially the fundamental theorem of arithmetic. You have n and you decompose it into its unique prime factorization, which is p1 power alpha 1, p2 power alpha 2, all the way up to ps power alpha s. Okay, for primes p1 all the way up to ps. Fair enough. Okay, and this alpha i's are greater than 0. Okay, strictly greater than 0. And define a function f that maps n to the sum of the exponents in its unique prime factorization. Okay, so next we define a sequence of sets given by s naught, which is just the singleton 1. And then we, for all m greater than equal to 1, we define Sm, which is all such natural numbers such that the sum of the exponents in their unique prime factorization is precisely m. Okay, so that's more or less the structure we need before we look at the two proofs. Okay, so now two more points that are to be noted before we dive right into the proofs. So the first point is that consider script p equal to the collection of the SIs that I've just defined. So the script p induces an exhaustive partition on the set of natural numbers. Okay, so this is an observation that any two elements of script p are mutually disjoint because of, again, fundamental theorem of arithmetic. And also notice that n belongs to S f of n, which further implies that the union over I equal to 0 to infinity Si is precisely the set of natural numbers. So basically, essentially, you can map any element of the natural numbers to some Si. Okay, so that Si is precisely I mean that I is precisely the sum of the exponents in the unique prime factorization of n. Okay, so 5 will be mapped to S1. Okay, because it's just 5 power 1, so the sum of exponents is 1, so it maps to S1. Okay, okay. So another small point, which is the infimum of Sm, that is greater than equal to 2 power n. I shall leave it to you to see this. This is very easy. Okay. So now we proceed to the proof. The second proof, as I call it, this is Arpan's first proof in his paper. So anyway, we will look at this. This is a very, very beautiful proof using just pure combinatorial arguments. Okay, so suppose there are k many primes. Again, we start with the finite assumption. Then clearly the cardinality of Sm is m plus k minus 1 choose m. So the author uses the word clearly, but I think you should try to figure this out. Why? Because I'll give you a hint. This expression, this m plus k minus 1 choose m, if you remember, you might have seen this expression in combinatorics, right? It is essentially the number of non-negative integral solutions to an equation x1 plus x2 all the way up to xn equal to k. I'm sorry, it's x1 plus x2 all the way up to xk equal to n. So it's the number of non-negative integral solutions to that. Okay, so there is another simple observation, which is there exists c greater than 0, such that the cardinality of Sm is bounded by some polynomial of degree k minus 1 for all m greater than equal to 1. So again, you can see this if you just open up the expression for cardinality of Sm, m plus k minus 1 choose m in terms of the factorials, and then look at the degree of m in that. Okay, so next in the paper, Arpan had left a claim, which is for every natural number, such an inequality holds. 1 plus summation of m equal to 1 to n minus 1, cardinality of Sm is greater than equal to 2 power n minus 1. All right. So he hasn't given any hint or any indication of why this inequality holds in his paper, but I think this is worthy of a proof. Okay, so this is how I have proven it. So this says that consider a set Pn, which is essentially 2 power n plus 1, 2 power n plus 2, all the way up to 2 power n plus 1 minus 1. Just remove the element 3 into 2 power n minus 1 from the set Pn. Okay? Okay, we'll see in a moment why we are doing that. So first observation that you can make on Pn is that the cardinality of Pn is essentially 2 power n minus 2 now, upon throwing away 3 into 2 power n minus 1. Okay, so what is our objective? Our objective is to show that this union m equal to 1 to n minus 1 Sm is greater than equal to the cardinality of Pn. So when you write down in this in terms of the inequality we have, I mean, if you write this down, I mean, this is a disjoint union. So this can be written down as summation of cardinalities. And if you write that down, then you will see that you will have precisely the inequality that we have been given to prove. Okay. So let L be an element of this set Pn, and let L be written as P1 power alpha 1, P2 power alpha 2, all the way up to Pk power alpha k. So notice that there is one small difference here. Let me go back to the previous page. Here, we actually had, in the fundamental theorem statement, we had alpha 1, alpha 2, all the way up to alpha is strictly greater than 0. Okay. So this was to account for the uniqueness. All right. But now, since we have, by assumption, we have only finitely many primes, we can keep them in the expression in the unique factorization. Okay. So if like you have say 6, then you can write it down as 2 power 1, 3 power 1, 5 power 0. Okay. So if you if those PIs do not appear in the prime factorization, you can just make them PI power 0. Okay. So with such a notation, we observe that L belongs to Si for some I equal to 1, 2, 3, dot, 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 n minus 1. Okay. So now again, why is that? Because the sum of the exponents of such a number is strictly less than n of a number belonging in Pn. Okay. So, and now you can possibly just try to argue, I'll leave it to you, that 3 into 2 power n minus 1 was the only nuisance creating element. So the sum of exponents for that is exactly n, for which our argument would have failed. So upon removing that, we can say that the sum of exponents is strictly less than n, and hence L belongs to Si for some I equal to 1 to n minus 1. Okay. So consequently, L belongs to their union as well, for m equal to 1 to n minus 1 union of Sn. Okay. This shows that Pn is a subset of union of m equal to 1 to n minus 1 Sn. All right. And now we are done, because we'll just take cardinalities on both sides. So we'll have our claim. All right. So once we have our claim, the proof is not exactly immediate. There are few more steps to it. So from the claim and the previous results, it follows that this expression on the left-hand side, 1 plus, it is an n minus 1 degree polynomial, I believe, that is greater than 2 power n minus 1. Okay. So the term on the left dominates 1 plus summation cardinality of Sm, and that is which is again bigger than 2 power n minus 1. So this term on the left is bigger than 2 power n minus 1. Okay. So that again 1 plus c times n minus 1 power k, that is again greater than the expression above it. Okay. So that is again greater than 2 power n minus 1, right? So now we have an absurd statement, because the statement, so c is a positive constant, right? So the statement on the right is a polynomial, while the statement on the, the statement on the left is a polynomial, while the statement on the right is an exponential. Okay. So for large n, the polynomial will get dominated by the exponential, and this inequality cannot hold. Okay. So again, I leave it to you to come up with a rigorous argument. Okay. So this shows that our initial assumption that there are finitely many primes, in particular k many primes, was wrong. Hence, the primes are infinite. Okay. So very beautiful proof. And I think that this relies on just simple combinatorics, and should be, I mean, the target audience for this proof is everyone who loves mathematics. Okay. So there is one more proof that I'll briefly sketch out for you. So the paper is just a 1.5 page paper with 2 proofs. Okay. So this is the second proof. I think you should give it a shot. Okay. And I'll give you a brief sketch. So again, suppose we start with the same assumption that there are k many primes. And okay, so it is easy to show for m greater than equal to 2k, it's just algebra, that cardinality of Sm plus 1 by cardinality of Sm is less than 3 by 2. Okay. So now this proof is essentially along the same lines as Euler's proof. So Euler's proof crucially uses the fact that the harmonic series is divergent. So does this proof. Okay. So consider the harmonic series. So now we have an equivalent representation of the harmonic series, which is 1 plus double summation I equal to 2 to infinity. N belongs to Si, 1 by n. I'm sorry, that should be I equal to 1 to infinity. That's a typographical error. So why is this? Because Si, S0, S1, S2, that induces a partition of the natural numbers. So this is just another way of writing down the harmonic series. Then we break this double summation down further into 2 more parts. All right. So the first part is I running from 1 to 2k minus 1, and the second part is I running from 2k to infinity. Okay, so why do we do that? Notice that the first two terms, that 1 and 1 plus the double summation I equal to 1 to 2k minus 1, this quantity is bounded, right? So if we are able to show that the second quantity is bounded, that would imply the entire sum is bounded, which would in turn imply that the harmonic series is bounded. So that would give us a contradiction. So we just need to show that tail sum running from I equal to 2k to infinity, that is bounded. So now for we had before we began the second proof, we had an observation, the second observation, that the infimum of Sm is at least 2 to the power n. So for every n in Si, n is greater than equal to 2 power I. So 1 by n is less than equal to 1 by 2 power I. So if you sum over Si, then what you get is summation n belongs to Si 1 by n is less than equal to cardinality of Si by 2 power I. So now use mod of Sm plus 1, I'm sorry, the cardinality of Sm plus 1 by cardinality of Sm less than 3 by 2 to get the result that this tail sum is bounded by cardinality of S2k by 2 power 2k plus 2k minus 2. Okay. Now, observe that this S2k is a finite set. Okay. So using this observation, you can see that this tail sum is also bounded. So if this is bounded, that would imply the harmonic series is also bounded, which is absurd. So this again shows that our assumption of finitude is again false. Okay, so that was all. So a purely combinatorial proof followed by a purely analytic proof. So I hope you all enjoyed this. And if you learned something from this video, then I would urge you to share it with everyone who loves mathematics, who does mathematics, and the entire mathematics community deserves to know that such beautiful proofs exist of such a fundamental result. Okay, thank you very much.